Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great honor and pleasure to welcome Sasha GOROKHOVSKY from my most beloved University of Colorado, Boulder. Sasha will speak about the Heisenberg calculus and cyclic cohomology. I believe that this is our first online talk about cyclic cohomology. Sasha, the Zoom is yours. Take it away.
Well, okay, Piotr. Well, thank you very much for the invitation and for the introduction. So I will talk about joint work with Erin van Erp. And the goal of my talk would be to derive a homological formula for the index of the hyperelliptic operator, which arises by the Heisenberg calculus. So the Heisenberg calculus here provides a setup, namely a set of operators for which we would like to compute an index, and cyclic homology provides actually method of computation. Okay. Now this problem has been studied previously by a number of authors, so I will say give a few more words about the historical background later, so probably not sufficiently detailed, but for now let me start with the general geometric setup. Okay, so we'll have a manifold M, okay, which so very soon will need to be compact of dimension 2n plus 1. Okay, and one form is called a contact form if alpha of h d alpha to the power n is nowhere 0. Okay. So an example, if your manifold is R2n plus 1 with coordinates z, x1 through xn, y1 through yn. This is an example of a contact form, and moreover, locally every contact form looks like this. So there is the version of Darboux theorem for contact manifolds, which says that locally one can introduce coordinates which will, in which contact form will have this shape. Okay. Now, with the contact form, we can associate the following objects, which will be important for this talk. First of all, well, is subbundle of the tangent bundle, where alpha is 0. So the contact condition means that this subbundle is actually, well, not very far from being integrable, right? So it's as non-integrable as it can be. Okay. And vector field T, which is called Rib field, which is defined uniquely by requiring that alpha on it takes value 1, so it's transversal to H, and substituted into the form d alpha, it would give 0. So in the example, in the canonical form, here d by dz is a Rib field. And tangent bundle splits direct sum of H plus one-dimensional subspace spanned by T. Okay. So non-integrability can be seen as follows. If we have two vector fields which are tangent to the kernel of alpha. Then if we compute the bracket, the point m, well, this can be obtained by evaluating the differential form d alpha on the values of x at the point m, plus it will have tangent term. Tangent here means tangent to h. Okay. So the form d alpha, which appears here as follows from the contact condition, is actually defines a symplectic structure on the bundle H. So, in other words, it's non-degenerate. So that I forgot here to write transversal vector field P. So if you compute a bracket of two vector fields tangent to H, then generally it will no longer be tangent to H, but rather transversal. And this is non-integrability condition. Okay. So again, the fact that omega is non-degenerate is just shows how often this happens. Okay. So this will be the geometric setup, and with such geometric station, one can associate calculus of Heisenberg differential and pseudo-differential operators. I will not say much about why this is, but just say that the reason it appeared was that, for example, boundaries of complex manifolds naturally have a contact structure, so question appeared in complex analysis in the work of Folland and Stein first, and then has been studied extensively by many people. Okay. So Heisenberg differential operators. Okay, so for simplicity, so I will consider only operators acting on either on functions, scalar or like systems of those, so acting on a trivial bundle. Okay, so Heisenberg differential operators are just the same as ordinary differential operators. And again, here, for instance, in the scalar one. So it's just some combinations of, compositions of vector fields acting on functions on differentiation. So what is changed and what gives the name Heisenberg is that filtration, which one considers on them, is different. So order filtration is different. So how it's different? Namely, if x is tangent to the hyperplane bundle H, then it's declared to be order 1. And if vector field is not tangent to H, it's declared to be of order 2. So order of the transversal rib field T is declared to be 2. So this again is with this differential operator of order K. Also, the differential operator becomes filtered algebra. And as in the classical case, one can consider the associated graded algebra. So it's an algebra which controls the calculus of the principal symbols of these operators. One thing which we can notice immediately is that unlike the classical case, this algebra will be non-commutative. And why? Because, so how do we see commutativity for the calculus of principal symbols of scalar differential operator? If you commute two operators, you get an operator of order, which is sum of the orders minus 1. In this case, as we have seen, if you commute two vector fields tangent to the hyperplane, so both of them of order 1, you actually get something priori of order 2. Oh, sort of tangent. No, right. Order most 1. Okay. So on the level of principal symbols, you have non-trivial commutators, so which means that the algebra is non-commutative. And moreover, this equality allows one to actually describe what the associated algebra, graded algebra will be very simple, namely the space for quotient out by operators of order k minus 1, we will just get polynomial, I mean, some symmetric tensors in vector fields tangent to H, right? So then you will also have symmetric fields tangent to H, but symmetric tensors of degree k minus 2 times t, which bring raises order by 2, and so on. And the relation, I mean, the relation in this algebra would be that. So first of all, this will be an algebra of sections of some vector bundle with algebra structured every fiber, and so algebra structure on the fiber is also have x and y. So the algebra structure is the quotient algebra is just defined by this relation. So what this algebra is just the universal enveloping algebra of the algebra, which I will denote T sub H, which is Heisenberg. The algebra defined by symplectic forms. So if you have any symplectic vector space, you can add one extra dimension and construct a algebra where commutator of two elements in the symplectic vector space is given by symplectic form times extra dimension. And I should say that T here is central. So you can easily follows from the identities defining contact form. Okay. So this is, however, will not be the form in which it would be convenient for us to think about the symbols. So let me try to give slightly different description. Okay. So the symplectic vector space, just so H here will be just one fiber of our subbundle H at a given point. So let me drop the point from the notation. So if H is symplectic, vector space, one can reduce a polynomial Weyl algebra, which is the quotient of the universal developing algebra of Heisenberg algebra by evaluating t to be equal to just constant I. So you can think about this as polynomials on duo of H, and the product is Moyal product. So it's explicitly given by this formula where bk are by differential operators. So here xi are standard.
Sorry, Sasha, what is this thing before beta? You have -1 to what power?
Sorry, absolute value of beta.
Okay.
So alpha, beta, multi-indices, and
there's some minus somewhere in the formula, right?
yeah,
EFDG minus D.
Yes, so -1 to the power absolute value of beta. I believe.
No, but it's not product of derivatives. Next line.
Yeah. Well, I
There's a
mean,
minus,
sorry, that's one line which got broken into two. Sorry. Yes, there is some coefficients which have some factorials and signs, and yeah, and indeed, yeah, let's say standard symplectic, well, let's say Darboux coordinates.
Excuse me, I think that it was about the minus sign between yes.
Yes.
Yeah, it looks like a dot, but it's supposed to be minus, right?
2 lines higher up, Sasha.
2 lines higher up. Here. Yes. What about it?
Where is your? I can't see your
Minus
d alpha f d beta g minus d beta f d alpha g or what?
In the second line,
this is minus.
In the second line defining bk.
Yes.
There should be some minus. Yes.
It's one line up, I believe. Circled. this is a minus.
Yeah, but
So-
we mean between these four terms, you have four partial.
Oh, no,
derivatives.
it's
here.
times.
Times, okay.
It's times, yeah, it's product.
It's quadratic in F and in G.
Mm,
Oh, it's not quadratic, it's linear in F and G.
no, yeah. No, you're right, you're right.
Too
Yes.
many F's and G's.
You're, yeah, I think that's
It's just right, plus
actually,
minus instead of
yes.
dot.
No, I don't know. Yeah. Okay, don't know what I was writing. I think,
Yeah, that one's good enough, is this?
yes.
Just stop here. Yeah.
You're right, yes.
Yeah.
And that. Okay. Sorry, okay. So let's see, yeah. If k equals 1, one should get Poisson bracket as a check that this still makes sense.
Yes, it does.
And yes, and yeah. And this is, okay, Mayal product. Okay, Mayal while product. Okay, so explicitly, again, this get homomorphism from this enveloping algebra into W of the W by, sending each x into x, which you view as a linear polynomial on dual of h, and t is sent into I. Okay. So our definition actually you don't get every polynomials because you get polynomials which are homogeneous with step 2 only, right? Because your p which has degree 2 is equal to I. Okay, and this will be one part for our symbol. We also have homomorphism of u of th into the opposite of the Weyl algebra, which is defined by sending t to negative I. Okay, so it's essentially equivalent to changing the sign of the symplectic formulation. The opposite one, so one gets actually the opposite. Weyl algebra. Okay, so for us, the principal symbol of Heisenberg differential operator. So again, the Heisenberg differential operator is just the ordinary differential operator, but what's principal symbol? Well, depends on the word Heisenberg would be the image of the map of operators of order k. So the universal enveloping of Heisenberg algebra at a given point, and this is mapped into W, well, plus W op via each of these maps. So in other words, principal symbol.
What kind of manifold are you on? What is your hypothesis on the manifold you are working on?
For now, just contact, but let me just say compact as well. Contact manifold, yeah. So first of all, yeah. So so it's definitely contact, and let's say it's compact as well. So this was irrelevant for now. So principal symbol.
Okay. Thank you, Sasha. Yes. We're talking about contact manifold. Okay, good.
Yeah.
Good.
Yes, contact and compact.
And compact. Okay.
Yeah, compact. Yes. Yeah. So principal symbol will be, well, okay, for differential operator will be just pair sigma plus sigma minus, where sigma plus is well well, so, and sigma n minus. Actually, I shouldn't use n because it's the dimension. Let me use n. And well, polynomial can be broken into the sum of its homogeneous component. Okay. Similarly, sigma minus can be broken like this, and the components which appear here are not at all unrelated. Actually, sigma minus m minus 2k is well, so the negative components are exactly the same as positive ones, but with occasional change of sign. So now, why would one want to retain the information about both halves? Well, for differential operators, this is actually completely not needed, because each of them, the positive and negative component, determines the other uniquely. But well, we will see that this is what we need to work with pseudo-differential operators, and this is just one of the possible description of the principles in algebra. So, which happens to be convenient for our purposes. Another discussion, for example, another description would be as in terms of the universal enveloping of the Heisenberg Lie algebra and so on. So this is equivalent, but this is the one which we found convenient. Okay, so for example, if just x is tangent to h, its symbol will be pair xx, and this will be the symbol for operator t. Okay. So now, claim is that this calculus can be extended to the pseudo-differential calculus, and one obtains an algebra, which is usually denoted psi sub h. I will often drop h because that's will be the only types of differential operators which we'll consider, which contains differential operators. Okay, and let me describe how the algebra of principal symbol looks in this case. And let me just, again, for simplicity, do it only for operators of order 0. You can expand it for operators of other orders by adding some homogeneity. So let's consider first of all non-polynomial Weil algebra, which will be subset now of smooth functions on H. Okay, and you have say A is there. We assume that A has an asymptotic expansion at infinity. But standard polyhomogeneous asymptotic expansion, which have but polyhomogeneous of with a step negative to, so it has homogeneous component of order 0, negative 2, etc. And asymptotic expansion is understood in the standard standard symplectic expansion for, say, pseudo-differential operators. So inside it, well, an important subspace will be say, algebra of Schwartz functions, for which asymptotic expansion is just 0. So the split expansion is actually label quotient of W by S. So product is still given by Mayow product. Okay. And algebra of symbols, we call it A of is again subset of well, again, algebra of principal symbols at a point is subset of W plus W op. So it consists of sigma plus, sigma minus, where first of all, sigma, unlike the case of differential operators, sigma plus, sigma minus are no longer polynomials. The elements of the larger Weyl algebra of just smooth functions, and this compatibility condition on the components is replaced by only compatibility at infinity. So sigma plus minus has an asymptotic expansion sigma to k plus minus, and sigma minus k is equal to -1 power k sigma plus to k. Okay. So I mean, again, so an example of such a symbols would be just a pair of Schwartz functions, right? For them, the compatibility condition here is just empty. Both of them have 0 asymptotic expansion. Another somewhat opposite example would be differential operator. Well, since I wrote it of order 0, set of order 0 differential operators is rather small, but it's easy to see how expanded for other orders and to incorporate differential operators as well. So the claim is that the standard, the differential theory, in large part extends to this complex. So in particular, elliptic theory extends. And if operator has an invertible symbol, then on a compact manifold, it will be Fredholm. So the question which I would like to address is to find a formula for the index of operator Heisenberg calculus with invertible principal symbol in terms of the principal symbol. Okay. So again, there was a number of works in this direction. So let me just mention a few of those. So Epstein and Melrose. Should probably initiated work on this index problem. So they did find formula for the case when both sigma plus and sigma minus 1 are Schwartz functions. Okay. So this in particular contains a much older case of Topless operators and Tedemon-Bell formula. Okay. Then, from a point of view of K-theory, this has been investigated by Eric Van Erp and Paul Baum. So I'm now going into the direction which is closer to our work and probably to the rest of people here. So from this point of view, this problem has been studied and completely resolved. This, however, doesn't quite lead to, I would say, to the formula, namely, given a symbol, write some differential form integrates over a manifold standard. So there are certain steps which are still left unresolved if one wants to pass from the K-theoretical description to the formula of the kind we want. Okay, and so Raphael Ponch applied techniques of Cohomology local index formula to this problem, and so did obtain a local index formula, but this is essentially computations in terms of the complete symbol rather than principal symbol. So the goal here is to obtain some formula of the kind of Atiyah-Zinger index theorem in the standard homological form, namely given elliptic differential operator in the classical sense. You know you can compute its index by computing Chern character of its symbol, which has something which has very explicit description modified by some characteristic class, and then integrating, obtaining a number. So Epstein and Melrose give an answer of exactly the same shape, but under this very restrictive condition. So essentially from work of Baum and Van Erp, one can conclude that actually, in a way, this is sufficient. One can deform any such operators to the one of the type of Epstein Melrose. However, I mean, okay, one knows the existence of such deformation essentially, but so, for example, non-local and priori not exactly clear how to do it. And from Ponch, one does get formula, but this involves complete symbol. Let me just indicate that first of all, the fact that one can write such a formula is actually quite. The fact that such a formula exists is just essentially automatic from cyclic theory. So. Namely, if one considers algebra of complete symbols, one can write a cyclic cocycle on it. Let me call it chi of, to be very local notation. Like this, where A, B are in the algebra of complete symbols, A capital, B capital as a lifts to operators, arbitrary lifts, and the result does depend on them, and trace head is extension of trace to a linear map from zero differential operator to complex number, well, continuous, perhaps. And then if U is let's just say Heisenberg elliptic, then U, which is class of U, the quotient is invertible. Therefore, pairing of chi with Chern character of U, which is chi evaluated on U inverse and U, will be, I think, up to a sign index of this operator. So the cyclic cycle chi on this quotient computes an index, in the sense that if you pair it with an invertible element, you will recover an index. Okay, so this, of course, is a very simple observation. Totally misses locality, possible locality, which is developed in Raphael Ponce's technique. But now periodic cyclic homology of the algebra of principal symbols is isomorphic to the periodic cyclic homology of the algebra of the complete symbols. And here we have class of the cyclic cycle chi. To it corresponds something in the cyclic homology of the algebra of principal symbols. And well, anything which corresponds to it under this isomorphism will provide you with an index formula, which would compute index of Heisenberg elliptic operator in terms of its principal symbol. Okay, so the fact that one can write such a formula is, in principle, is clear. So the question is only how to do this. Okay, and that's what I will try to describe in the remaining time, and then maybe just briefly comment on the proof. Okay, so let me now describe the index formula. Okay, so sigma h denotes the algebra of principal symbols. Okay. Sigma h is the algebra of sections over M of some bundle of algebras, where H at the point M is what was just described before. It's a subset of set made of pairs of symbols which sits inside the Weil algebra direct sum with itself. Okay. Now some general setting of how one can compute something about cyclic homology of this algebra. So assume that A is some bundle of algebras over M. Okay, and assume that we have the following data. So nebula is connection on A, well, which acts by derivation. Theta is some two form with values with A, so that the square of nebula is given by the brackets with theta, and satisfies this condition, right? Notice that theta is not uniquely determined by nebula. A priori, it has to be specified as part of the data. You can alter theta by any central valued closed form, for example, right? Both of the conditions will be satisfied. And tau is fiberwise trace on A. Which satisfies this condition. Okay, so I think we will construct all of this data for the algebra of principal symbols that's described. But once we have all this data, what we can produce.
Excuse me, Sasha.
Oh, yeah.
I just didn't quite understand the last formula. What is the term on the left? Before
Tau
the
of
connection
nebula
of A? What is it?
Oh, so I'm sorry. So nebula A would be one form with so A is a bundle.
Oh, it's a T.
Right?
It's a T on the left, I guess, or what?
Oh yeah. So it's tau. So tau. So
I see. Tau.
there is the same letter on the left and on the right.
Oh,
yes.
okay.
So
good.
it's okay. So it's the same. It's basically the condition of the trace being closed, but again.
Okay. Good. Thank you.
Fibered condition. Yeah. So with this we can produce again, produce a map from the cyclic homology complex of the algebra of sections of A into different in the RAM complex of M, just by simple explicit formula. Let me call it T, hopes that it will not be confused with a Rib vector field. So some coefficient, some sign, so the sum is finite because the degrees of forms on the right keep increasing, so they'll terminate after so finitely many terms. Okay, so we get a morphism complexes. Okay, so we can having all of this data in place, and as we will have our algebra of principal symbols, we can produce this map, and then we can construct, as usual, a map from K-theory of the algebra of principal symbols into cohomology. So I will denote it Chi. So Chi appeared before here, but I think that notation is now retired. So from the map from K1 of our principal symbol algebra to the cohomology, and if you start with class of an invertible element here, so let's say Heisenberg elliptic symbol, well, it goes maps into Chern character, which is an element. Into cyclic periodic homology, and then via the map T, it maps into homology of M. Okay, so well, this map is again described by explicit formula. Essentially, U is mapped into sum of tensors of this form with certain coefficients. Okay, so the index formula which we have is that if D is Heisenberg elliptic, then index of D is equal to integral over M of this chi applied to principal symbol wedge A hat of M. So the only thing which I think remains for me to do now is to describe the ingredients in the formula. Namely, I need to tell you what is a fiber-wise trace, what's connection, curvature for this algebra of principal symbols, and then say a few words about how one can verify this formula. Okay. So let me start with the trace tau.
In your formula for the index, where is the trace? Is it in the chi? Where is the trace?
Yes. Trace is in the chi. Sorry. So let me backtrack a bit. So chi is a composition of the map T, which is in the upper left corner, right? And this is a formula which involves trace. Okay. So this map T, which essentially map T starts with, so you start with the principal symbol, where cyclic Chern character you write symbol inverse, right, the standard, and then you apply to it connection, multiply by curvature, get some expression, and then you apply the trace tau. Okay, so all the three ingredients actually enter into this map from cyclic complex to the de Rham complex. Okay, so this is where we need to have them to write the result. Okay, so tau. First of all, let's start with so tau is a fiber-wise trace. So let me just work on a single symplectic vector space. Okay, so and let me drop the point from the notation, and A, let me remind you, was a subset of A consists the algebra which consists of pairs of elements in Weil algebra and its opposite, some compatibility condition on their behavior. First of all, let's start with defining something on just a single copy of the Weil algebra. If you have an element of Weil algebra which is a Schwarz function, so there then on the Schwarz functions you do have a trace, which is just integral of your function. Okay, so didn't play any role so far in this discussion, but it's explicitly implicitly Topless, but Weil algebra of course is represented as operators acting on two of Rn, and this is just the usual operator trace. Okay, so now let's extend it to the entire W, not as a trace but as a linear function. So we need to regularize it in some way. So choose some metric on H. And if A is now an element of W, compute the same integral, but now over the ball of radius R. And what you will get, due to the asymptotic expansion of A, will be some polynomial in R. Then you may have a log term, and then you will have something which remains bounded. So define the regularization of the trace to be just what you get from the bounded component. So we remove all the divergences and compute the limit. And such a limit will exist due to the asymptotic expansion condition posing on A. Namely, at infinity, A has to behave in a certain way, which guarantees existence of such asymptotic expansion. And for Schwarz function, you do recover the old trace. Okay. So now this trace tilde, of course, will no longer be a trace on the algebra W, well, it has no traces. However, the main issue here is the presence of the logarithmic term. Okay. So now if we have this pair sigma plus sigma minus in A, we can define, so sorry, where A is this pair, tau of A to be the difference of the regularized traces of the components. Well, turns out that now tau is a trace on A, moreover, symplectically invariant. So it doesn't depend, for example, on the choice of metric, which we did. It's completely canonically defined. And
is it unique with such properties, or how unique is it?
Yeah, no, I think it's okay. As far as I remember, yeah, it's not hard to compute a cyclic theory for this algebra, and it has a unique trace. Yes.
Okay. So
So yeah. So 90% certain, but I haven't looked at it recently. But yeah, I think it fits into the natural,
Okay.
right? Two algebras glued over a third one have along exact sequence, and the existence of the trace.
It is unique, actually.
It is unique. Okay.
It is unique.
Okay, good.
Yeah. Yeah. So unique and and therefore canonical. Okay. So other ingredients is just connection and curvature, and these are well, somewhat possibly more standard to define. So symplectic algebra acts. So again, we are on a single symplectic vector space. So symplectic algebra will act on A. Now inside A, well, not quite inside A, but can slightly enlarge A. Say by adding. So previously our algebra consisted only of say pairs of smooth functions which admit polyhomogeneous expansion of with homogeneity 0 or lower. So let me add positively homogeneous term. Okay. So then speaking properly, this should have been done probably at an earlier stage. Okay. Then in particular one can consider homogeneous quadratic polynomial. With commutator and checks that commutator of two quadratic polynomials again quadratic, so one gets a Lie algebra. Moreover, isomorphic to SP, and from the again the action of this Lie algebra on A by commutators coincides with the action of the symplectic Lie algebra. So this is what induces isomorphism. So if you have nabla, which is a symplectic connection with theta SP valued curvature, then one immediately obtains from it connection with the value of the Lie algebra of quadratic polynomials. So let me give some name to this Lie algebra. Let's call it G. And G is actually subset of A, advanced one if we put quadratic polynomials in it. Okay, so this is what's the standard construction. So this isomorphism of the Lie algebra of quadratic polynomials with the symplectic Lie algebra is what what one does to construct a metaplectic group, metaplectic representation, and this discussion is entirely parallel to the discussion of spin structures that leave each with a connection to the spin connection. So I think I will skip the details here. So let me just say that it's easy to verify that what one gets satisfies all the necessary properties. And let me just make a few comments about the proof. Okay. So the proof essentially consists of verifying the formula for sufficiently many examples to see that it gives correct answer when it should, and concluding that this therefore gives correct answer for every elliptic Heisenberg operator. Okay. So what are these examples? So there are two kinds. So one is actually Topless operators. So which actually are, I think, on the boundaries of some complex manifold. That was, I think, the very original example. So there is essentially canonical, semi-canonical projection inside the algebra of Heisenberg with the differential operators. So it's called Seger projection. Okay, and one can associate with it Topless operators. Where F is, well, here I probably should write a matrix of functions. So it would be important now to act on not just on functions, but actually on sections of trivial vector bundles. And first of all, Topless operators will be Fredholm if F actually is an invertible matrix. And then its index can be computed by this Boutade-Monvel formula. Which is probably the original formula in this direction. So for in the context of, it has been extended to the context of contact manifolds and possibly by Epstein models. Definitely an operator of the kind for which we computed index. Okay. Now, in the usual manner, one can associate with it Heisenberg elliptic operator. I should say that TF acts as usual on the range of S, so can make it act everywhere by adding to it 1 minus S, and indexes of operators are the same. Okay. So one needs to verify that we get the correct answer if we apply our formula to this case. And so the principal symbol of the Sega projection just up to a constant Gaussian the first component, well, up to some constant, and 0 in the second. Okay. So we therefore need to compute our map chi applied to f times principal symbol of S, which happens to be Chern character of K-theory element associated with F times chi of S. And finally, chi of S can be computed by explicitly, and this is will be just exponential of the first Chern class of tangent bundle of M over 2. Okay, by the way, I should mention that, talking about Chern classes, and here third class of M, so it's third class of tangent bundle of M. So we've seen that tangent bundle of M is isomorphic to some of symplectic vector bundle plus one-dimensional bundle spanned by the vector field T. So symplectic structure defines an almost complex structure, just on H up to homotopy. So with this choice, H becomes an almost complex vector bundle. So one can define third class and first Chern class using this almost complex structure on TM. Okay, and therefore, by our formula, we get precisely the relevant third class. Okay. So this verifies that in the case of Topless operators, our formula gives an answer which agrees with whatever in the formula. Second class of operators are the morphisms vector bundles. Okay, where we would expect to get an answer 0, and once we plug everything into the formula, this computation amounts to computing tau of powers of the curvature. Now, let me remind you that the curvature was acting as a differential operator, right? So the differential operator, so it corresponds to a polynomial element in our algebra A, and I backtrack a few slides. Our regularized trace was computed as follows. You would computed as follows. You would take A, which in our case is a polynomial, integrate over a ball, and then remove all the divergent terms. So for polynomial, clearly you will remove everything. So trace tilde is 0. So regularized trace of polynomial is 0. Therefore, tau of polynomial is 0. Okay. So again, what we get from our index formula for the endomorphic vector bundles is 0 index, as expected. And finally, it shows that every element in K-theory of the algebra of principal symbols is a sum of classes of symbols of Topless operators and endomorphisms of bundles on M. So these two classes of symbols for which we verified our formula actually generate the entire K-theory of symbols. That's since our formula gives correct answer for those operators, it would give the correct answer for every K-theory class. Okay, so I think that's all for me, and yeah, I can stop right here. Thank you.
Thank you very much, Sasha. Let's clap hands. Here you go. And now we can start further questions. So please fire at will. Any questions to Sasha? Go ahead.
I have a question about, wait, can you hear me?
Yeah, we can hear you.
I have a question
Yeah,
about
yes.
your formula. You have the A hat class. This is the polynomial Pontryagin classes, right?
Yes.
So in particular, it just appears in dimension divisible by 4. But in the formula for the Topless operators odd class,
Yes.
are you sure you have the correct character? I mean, it will be some characteristic class, but are you absolutely certain that the A hat class is the correct characteristic class?
Yes. Yes. Actually, let me tell you why. So yeah, well, as about other things. So let me maybe again just say one word about the difference between A hat and Todd once it goes through. So our formula, right, has two elements. One thing which I called chi, right, and one thing which I called A hat. So chi also, in a way, chi content. So
I see. I think I do. Chi is building in the first Chern class. This is what you are saying.
Yeah. Yes.
Within it, the first Chern class, and that makes that. And it's correct. Yes. Okay. Very good.
For example, here. Yes, and maybe one addition is that here we looked only at. You see, there are really two almost complex structures on H, right?
Okay. Yes.
The one we used and the opposite one. Okay. So for the opposite one, chi gives exactly the correct negative first Chern class. Okay. So this discrepancy between, so in principle, one has two different Todd classes, which one can reasonably write, depending on the choice of almost complex structure. One doesn't see this difference in our formula in the sense that it's kind of, it appears in the calculation of this character map chi. It returns exactly the correct Chern class depending on the complex structure.
Okay, I have a second comment, and then unfortunately I have to. Thank you for this very interesting talk. This was very interesting. Very good. Quite interesting. So when Eric Venerup and I studied this problem, in particular on odd dimensional spheres, right? I mean, these are basic examples of contact. We got some very simple explicit formulas for what's happening with some of these interesting Heisenberg elliptic operators. Of course, they are not elliptic in the usual sense.
Yes, yes.
They are Heisenberg elliptic, which means that they are not elliptic in the standard sense. On odd spheres, we got very explicit formulas for these interesting operators that appear on the. So this. And it involved Bott periodicity and so on. And it should come out of what you are doing. Those same formulas on odd spheres, which are very simple formulas, should come out.
I believe, and here, I say that for big part of it, I believe Eric. So that's what one recovers. Yes, I believe from. So it's relatively easy to do the explicit computation here as well. So one does get very explicit formulas.
Very good. Okay, thank you. Thank you. Thank
you.
Okay. Anybody else? Alain, would you like to ask?
No, Raphael has a question.
Oh, sorry, I didn't know.
Oh.
Yes, go ahead, Raphael. Go ahead.
And you have to put your microphone. Yes.
Yeah, I am asking him to unmute.
Oh.
You are muted, Raphael.
Oh, I see a hand, but yeah, I don't hear anything.
All I can do, I can ask him to unmute. I cannot unmute anybody against his will.
Yeah, we cannot hear you, Raphael.
Raphael.
Okay, so in the meantime, let me ask a question, which is probably easy to answer. I mean, there is some similarity between the regularized trace and the Vodiski residue. Can you say more about this?
Actually, I would say that this is not Vodiski residue.
No, it's not. But what I mean there is a strong similarity. Yeah.
Yeah. So actually, I think what happens here is that we have to. So one can define this trace rather differently,
yes.
But exactly in parallel to Vodiski residue, namely use harmonic oscillator to write a zeta function.
Yeah, sure.
So in that way, for pseudo-differential operators on Rn, one defines Vodiski residue. So this trace actually is the next term in the
okay. It is the next term. Yes, it is the next term. That's what. That's I would agree with that.
Yeah. So, but maybe just one comment is that it is a trace because when you combine the two halves, Vodiski residue
sure
cancels. So that's
exactly. Yes.
But so it's
okay. So I think Raphael is going to type.
Raphael.
Hopefully.
Because he cannot unmute his iPad.
Yes, iPad.
I switched to.
So Raphael.
Ooh, there's a very bad echo.
Because
Raphael, you have too many devices at the same time.
I guess should be better now.
Yeah. Now we can hear you well. Yes.
And okay. I don't have a question actually.
So what's the question?
I don't have a question.
Comment?
You had the raised hand. I mean, so that's why we thought you had a question. Yes.
No, it was to.
That's what I thought.
Oh, I see.
Hello, that is what I thought. That's why I didn't know.
Excellent. Okay, excellent.
Anyway, I have a comment. I think it's a question which is still open. Is to show that the non-commutative residue of Heisenberg projection is 0 or not 0.
Sasha, now you are muted, and I see you moving your mouth.
Now you are muted.
Yes. No,
Please unmute. Yeah.
actually, you haven't missed much. I was saying that yeah, I have nothing new to report on this on that question. Yes.
But it's something
That-
you're working on, or
Oh, so
No, but
yeah, I think potentially. Yeah. So I think that's a question which we were talking about for a long
Is it-
time, and it's.
with the work with
No,
Henry that you had
in
done?
principle, knowing the homology class. So I would say that yeah. So anyway, so for Heisenberg calculus, I cannot say anything new on this topic. Yes. So in principle, no. I mean, one has a complex of cyclic complex of arbitrary order operators contains the subcomplex of zero filtration subcomplex made of only say operator or as a complete symbols of total order 0 less, and in principle, knowing what would be homology class of residue in this complex gives you complete information about all index formulas and say residue of projection, etc. But yeah, I think what we know so far that doesn't answer this question. That doesn't tell you what this class would be. So, yeah, no, nothing new about it. I think it's a good question.
okay, Rafael, are you happy with the answer for the time being?
Yeah. Well, it's kind of a problem to suggest to work on.
Yeah, no, yeah, I would agree. No, thank you. Yes, I think so. Short and honest answer is I don't know.
Yeah, sure.
Yeah.
Richard, you look like you want to ask a question.
No, I don't.
You don't.
Okay.
Anybody else? Tomek?
Not
go
at the
ahead.
moment.
Can I?
Yeah, sure, go ahead.
So I have two
Oh.
questions. So probably the answer for the first one is obvious, and maybe the second question is stupid, but I don't know. I cannot resist. So the first question is why this filtration is such that the order of this rib field is 2. Can this 2 be replaced by some other number?
Well, no, I mean, yeah, no, you needed to be filtration on an algebra. It's yeah. So there are some verifications which I skipped, right?
Okay.
So which is this actually does, yeah. So
Okay.
then
I see. So the second question is, what if you replace this contact form by its multiple, positive multiple of it?
Yeah.
The filtration will be the same, the graded associated algebra the same, everything will be the same. What about these asymptotic expansions?
I think yeah, it's the same. Yeah. So I think
Everything the same.
so. Yeah, you can multiply it by a positive function and nothing.
Sasha, there is a related question to this question, which is, what about the role of the choice of the Reb vector field? I mean, what role does it play?
Oh, I'm sorry. Could you? Yeah.
Yeah, what I was saying is that, you know, you were choosing this Reb vector field T. So, I mean, the choice is not unique. So, I mean, what role does it play? I mean, moreover.
No, actually, no.
It plays no role, you mean? Yes.
No role.
Just convenience, you mean? You just choose it as a supplement, yes. Okay.
Yeah,
Okay.
so yeah, precisely. It was just,
Yeah.
so I think,
Yeah.
so orientation, I mean, again, T going to negative T would change some
I understand. Well, in
signs,
fact, you
but
know,
not more.
I have a more general comment, which is that, I mean, okay, it's nice, of course, to verify, as you say, you know, so it's more at the end, what you do is you check that the formula is correct. But I mean, which is different from making a new proof somehow, if you want. You see what I'm saying. And
yeah.
and what I'm what I am curious about would be, I mean, more in the directions that Raphael has pursued and so on, and more also in the more geometric framework where you would use the adaptation of the tangent groupoid to the Heisenberg calculus. I mean, so that would be more my question, in the sense that, I mean, it would be nice to have something which is closer to a proof and that actually uses geometric framework.
No, I agree, and yeah, we're definitely thinking in this direction. Yeah, so hopefully, yeah. I think, yes. So somehow to, again,
But I mean, of course, it's very important to have the formula. So okay, that's fine.
This is not intended to be the
final
for the final word. Yeah,
I
think, This is definitely no. Thank you. Yeah, that's I would say definitely.
Mm-hmm.
Yeah, I think there's some existing work with which it would be better to, to understand connection, and there are some, I would say, actual questions.
Can I ask another question?
Oh, please.
In your calculus, you are using the framework of curved DG algebras. I know that there's a well-developed homotopy theory of curved DG algebras. Can you do something in this vein before going to this de Rham calculus to compute some invariants, taking values in this homotopy class of this curved DG algebra?
Yeah.
Before you are applying this this trace to make them differential forms.
So, in the sense that this is not exactly the answer to your question, but I think it's points toward it in the sense that I think everything that I wrote is well defined on homotopy classes of DG algebra. So these formulas which I wrote there, they kind of, in a natural way, they behave well with respect to this homotopy theory. So so they are defined on these homotopy classes, and it's so which suggests that indirectly suggests that the answer should be yes. To your question should be yes, but
but then I wonder what could be the analog of the integration of forms against the fundamental class of the contact manifold on the level of this algebras, curved DG algebras. What is this?
Oh, it should be the power.
Yeah, I would guess that there's some additional structure, right? Which you can impose in greater generality, but priori,
So it would be something between pairing with Cohomology class and integration along the fundamental cycle of the contact manifold.
Actually, I think so. There would be some additional, some kind of a trace which is not part of the normal definition, but this formulas. So there is some not entirely trivial fact as far as I could see that this actually does seem to drop somewhat further than just plainly homotopy theory. Namely, I think there might be a center on curved algebras, and things somehow descends on the quotient by the center, but on the level of explicit formulas in cyclic theory, they get actually they're not terribly complicated, but they're not entirely trivial. So, so in that sense, one depends on homotopy class and even something slightly coarser than that. But I would think that this integration is something like a trace, which is additional structure which you can I mean, add, but it's not part of the definition of curve DJ. No, but you can. It's easy to see what it should be.
Yes, but I wonder if this integration, let's say integration of curved DG algebras could be realized in terms of this contact structure.
Shouldn't it be related to the tau that you were constructing?
Yeah, no. I mean, I would say that in a way. Maybe I'll say what the classical parallel, right? One can have a differential graded algebra, right? Or one can have a differential graded algebra with closed trace, which would give a cycle for, you know,
yeah, so it's exactly the beginning of cyclic homology. You know, the differential graded algebra with a trace, of course, yes, with a graded trace.
So in that case, but this graded trace is additional structure. It's not just something which is different. It's differential graded algebra plus additional structure. So I would say that similarly in this case for curve DJ, you can impose this additional structure. And homotopically, I think you don't get again, you know, by this construction again. I think in the original paper of N, you know, you can straighten the curved VGA by, you know, introducing this extra work. So I think on that level, I don't think you get different homotopy theory, so that you get bigger class of, you know, classes, which some of which appear naturally, but in the end you end up with the same cyclic theory. Right? So I think actually, if you look this homotopically, you should just bigger set with, you know, again with homotopies, but everything should be just represented by ordinary DGAs with so ordinary cycles for cyclic theory. So I think that's what it should all boil down to.
So you think that there's no separate theory of, let's say, closed graded traces for this curved CD?
Curved. So if I am to make a guess, is that you have a bigger, you know, a larger set, homotopy on it, but everything can be, you know, represented by this, by exactly what's in this, you know, in the IHS paper, you know, cycles for cyclic theory. So every representative, everything can, so it should be exactly the same homotopy theory.
Yes, probably.
So again, the reason to look at PRDJ is that, you know, okay, so from geometry you naturally get this as an input, right? But and the whole point is effectively to move it into the standard cyclic framework and do some calculation, because that works well with cyclic theory and so on. So I think the reason for this is not that you get a different theory, but rather the precisely to get exactly this same theory. It's just that the geometric data feeds you this curved data rather than just directly the cycle. So anyway, I think that's just general description of the picture.
So
thank you.
So if I understand, so you have the symbols such as the section of bundle of Heisenberg algebras.
Yes.
Right. And then the way it happens that if you look at 0 for the symbol, then at each point you just have this formal difference of something sitting at -1 and +1. Right.
Okay.
So the 0 for the symbol is basically given by the pair of I know symbols, one for central character -1 and one central character +1. Right? And then when you write down your index, you just write down the cyclic.
I missed your question.
No, question is so whether your index formula is basically the cyclic cycle on the Heisenberg group, but represented on the zero homogeneous symbols. So depending on the +1, -1 value. Right, instead of writing down cyclic cocyclic Heisenberg group, you restrict it to a kind of zero homogeneous elements of a Heisenberg group.
So I would, so Richard, so first of all, I need to apologize because I heard, yes, due to audio quality, I missed some parts of your question, but so let me answer what I think it is. So this representation as a pairs is just one possible one. I mean, it works well. Maybe others as well. So what
but this representation
if one Fourier transform.
No, wait a minute. So this representation is representation for a zeroth order symbol, right?
Yeah, but actually I should say that zero is not truly critical in the sense that you have it for other orders as well. I just wanted to.
Yeah, but still, homogeneity. If you assume homogeneity, but you just need values of at central character -1 +1, right?
Yeah, that's correct. But actually, but I should say that this tells you what it does in every representation, right? Because
yeah, sure.
That and this kind of this hyperplane of representations, your plane is a limit. That's precisely symptotic expansion. But you can view this as do Fourier transform, view this as a distribution on the Heisenberg group with very precise singularity at 0, and that might be a different way of looking at exactly the same algebra. Possibly that's again here it was convenient because again some of the formalisms seem to be easy to write using this representation, but I don't feel we are far enough to claim that other descriptions are somehow
no. But what I'm trying to say is that it's kind of, so you have this 2n + 1 cocyclic Heisenberg group, right?
Yes. So
there's only one, right?
Yes.
It's cyclic cohomology is one-dimensional. Cyclic cohomology is one-dimensional. So you have this 2n + 1 cocyclic Heisenberg group, and you're actually representing it on you fix homogeneity of your operators, and then you can represent it as something evaluated on -1 and +1 central character. Isn't that what's happening?
Cohomologically, probably yes. Right, but so I still not certain because of this is not quite Heisenberg group convolution algebra. They are singular at 0, right? So
yeah, but that's this homogeneity problem, right?
Again, on the common part for every so I would say that first of all, on the common part where everything is defined, this should be exactly what you say, and I mean again, and probably what you are saying is can be made correct literally, but I need to think a little bit more.
I don't know,
that.
just as feeling. So
no, I would agree in this, but I looked at this a little bit, and I don't know how to make it
literally correct.
I have exactly the same feeling, but at least I mean, short attempts to do it don't. I mean, again, so far I don't doubt that something like this should work, but it needs a little bit more work. And again, I think as a byproduct, I mean, again, the main interest is as a byproduct, it would just eliminate all this discussion about checking it for variant for Topless operators, just essentially give a version of a complete proof and possibly somewhat. So yes, so that's definitely something worth. I mean, something I try to look at, but yeah, so far so it needs more work so far.
So, okay.
Okay, anybody else? I don't see any raised hands. So if not, let us thank Sasha again for all his efforts. Yeah, thank you so much. Yeah. And yeah, let me remind you that in a week we'll have a spectral triple talk by Adam McGee, and it's going to be different from the talk he gave some weeks ago at the other seminar. And also let me remind you that tomorrow and the day after tomorrow at the Banach Center, Andrzej Sitarz is running a conference again on spectral triples. And in the announcement there was, Andrzej, do you want to add something?
Well, spectral geometry rather than spectral triples.
Okay, spectral geometry.
Talks by Bruno Jochum, Thierry Masson, Dmitry Vasilievich, Masoud Kalkali, Yang Liu, and Michał Wrochna about the spectral action. The last one was about the spectral action for the Lorentzian. So, interesting. 3 talks a day, 2 days, online at Zoom. Go to the Banach Center. And
you have to register. It's not trivial, right?
Going to the Banach Center.
No, registering.
I do apologize. This is, the Banach Center, stuff. I can send you, if you want to register an easy way, an absolutely easy way. This is just.
Yeah, please send us the easy way.
Yeah, exactly.
Easy way means easier than at Banach Center without, giving your credit card details or whatever is required there.
Please, yes.
No. He's making it up.
This is joking, but just putting your email. I put the link so you can go to this sort of simpler thing and fill in the form, and then what I need is just an email so that you're interested, and I send you the Zoom link.
Yeah.
It takes 2 minutes to register.
Yeah.
Yeah.
Okay.
Yeah, because the registration is only so that you get a Zoom link. And I understand Andrzej didn't put it on the web page because you're afraid of being trolled.
Yes, Zoom bombing happened, to things that were put public by some teenagers or whatever, whoever that was. And that happened, so we refrain from putting the Zoom link available, in advance. What we might do, we might put, the Zoom link, be something like 2 minutes before or 10 minutes before. But since this is the same Zoom link for 2 days, that would make the second day, also sort of as an easy target.
Yeah, but with Banach Center registration, not so horrible. Just put your email, you put some password which you can make up, any password, and then that's it, because all other questions are irrelevant. Do you need a visa? Do you need a hotel room? I mean, almost everything you don't need to fill in.
Yes, they do ask about hotel room, yes?
Yeah. I do just ignore it. You write your email and that's it. That's your registration.
So if you just want to put your email, I send the link on the chat. I mean, Francesco, earlier by mistake, I just sent it to Francesco, and Francesco already registered. But now the link is there to everybody.
Oh, so, yeah, there is a page, your private page.
Yeah, my private page, when there's form, sort of very easy form when you put your name and click, and that's it. So no need to put your arrival date or departure date.
Well, you have to put arrival day and departure date.
Yeah, you
right?
had, but I said that, yes, I had to put arrival and departure date. That's true, yes. Yes.
Well, it's not really relevant, right?
Yes.
No, Richard, you can be creative about it.
I was, believe me, I was.
Good.
Very good. Yeah.
Okay, guys, so if not tomorrow, I hope to see you in a week at Adam McGee and Spectral Triples and perhaps even tomorrow. So thank you again, Sasha. It was
Sasha,
a pleasure
thank you.
seeing you.
Thank
All
you.
the best,
Thank
guys.
you,
Thank you,
everybody.
Ferdinand.
Attention.
Thank you for coming.
Thank you.
It's great to have you here.
Thank you.
Bye-bye.
Thank you.
Bye, guys.
Bye.
Bye-bye.
Goodbye.
Bye.
Bye.
Bye.